This presentation is part of the WEC Sim training course. My name is Jorge Leon and I work for Sandia National Laboratories and I am part of the WEC Sim development group. Today I will talk about Vimeo. So first of all, what is Vimeo? Vimeo stands for Boundary Element Method Input-Output, and Vimeo is a set of functions that are used to preprocess the VEM hydrodynamic data prior to running WEC Sim. So how the workflow looks like. So first, you need to run your boundary element method for your geometry. So you can use your any of the available software such as WAMIT, NEMOH, Captain, or AQWA. And the output of the boundary element method is the input for Vimeo. Then the output of Vimeo is what WEC Sim takes as an input. So Vimeo is in between the VM and WEC Sim, and it helps WEC Sim to understand the boundary element method outputs. So the purpose of Vimeo is to read the VM results from WAMIT, NEMOH, Captain, or AQWA. It calculates the radiation and excitation impulse response functions. It calculates state space realization coefficients for the radiation IRF, and Vimeo saves the resulting data in the HDF5 file data format. So also Vimeo plot typical hydrodynamic data for user verification. So when you run Vimeo, what you will have after you run Vimeo is that H5 file and also a MATLAB data structure that we are going to call a hydrostructure in this presentation. So the location of the Vimeo functions are in the WEC Sim main folder. Then you go to source, functions, Vimeo, and then that's where you can find all the different functions that Vimeo has. We're going to talk about some of these functions, and we're going to give you some examples as well. For the documentation for Vimeo, you can go to this web page. Is the main WEC Sim documentation web page, and then if you go to advanced features, you can find all the information for Vimeo. So now I am going to talk about the different functions that Vimeo has, starting by this function, readWAMIT. So this function, it is used to read data from a WAMIT output file. So it has three parameters. So the first parameter is a hydrostructure. So you will need to create this structure first, like in this example here, and then you need to pass that as an input for the readWAMIT function. The second input is the file name. So you need to specify the name of the file that you are going to use, in this case your WAMIT output. And there is a third option if you want to read the excitation force coefficients. We also have a function to read hydrodynamic data from NEMOH. So you can use this function if you have NEMOH results. So you need to define first, for the parameters, you need to define first your hydrostructure, just as the previous example with WAMIT. You need to define also a file name, but in this case, instead of defining just one specific file, you need to define the path to the NEMOH working folder, to the complete NEMOH working folder. So, and this folder needs to include some specific files, such as the NEMOH.call file. You need to include also the hydrostatics file from NEMOH, the KH file, and some others like the radiation coefficients, .tech, and the excitation force, .tech. Also, some additional files that you may have and you can use with this function is the diffraction force and the FK force. So if you don't have this file, you still can run the readNEMOH function and it won't complain. But if you have it, it will add this information into the output structure. We also have a function for AQWA. So this function reads data from AQWA output files. So it has a similar implementation as well. So you need to define first your hydrostructure, and you need to define two file names. You need to define the .ah1 AQWA output file and the .lis AQWA output file. We also have a function to read the results from Captain. In this case, again, you need to define your hydro structure and the file name for the Captain.nt output file. We also have this function called combine VM, and this function is used to combine multiple VM outputs into one hydrodynamic system. So if you have different VM runs for different bodies and you feel that there is no a strong hydrodynamic interaction between these bodies, you can use this function to combine them into just one hydrodynamic system. So this function requires that all VM outputs have the same water depth and same wave frequencies and same wave headings. So the next function is radiation IRF. So this function calculates the normalized radiation impulse response function. This function is calculating this interval here numerically. So the parameters that you need for this are first your hydrostructure as usual. So you need to define this hydrostructure here again. You need to define dn, which is the calculation range for the impulse response function, where the IRF is calculated from 0 to the time that you define here. The default value is 100 seconds. Also, you need to define the number of time steps in the IRF. The default value is 1001. You need to define the number of frequency steps used in the IRF calculation. The default value is 1001 as well. You need to define also the minimum frequency to use in the IRF calculation. The default is the minimum frequency from the VM data, and you need also to define the maximum frequency to use in the calculation, and the default value is the maximum frequency from the VM data. So what this function is doing is that it's taking the coefficients from the VM and is calculating this equation here numerically. So these are some of the results that you have from the VM and from BEMIO. These plots are calculated with BEMIO. So then you have here the normalized added mass and the normalized damping. So we are using the normalized damping coefficient to calculate this equation for the impulse response function. So here you need to make sure that this variable here is less than the time for the convolution integral. You need to define the time for the convolution integral also as an input for this function. BEMIO also has a function to calculate the state space realization of the radiation IRF. This function is useful because it runs a lot faster than the previous function that I just mentioned, the radiation IRF, and the parameters that this function uses is the hydrostructure, the maximum order of the state space realization, which the default value is 10, and also the R2 threshold, the coefficient of determination for the state space realization. This value can range from 0 to 1, and the default value is 0.95. We also have a function to calculate the excitation impulse response function. In this case, the parameters are similar to the ones that we are using for the radiation IRF function. So we have our hydrostructure parameter, we have uh, the final time for the calculation of the IRF, we have the number of time steps, the number of frequency steps, the minimum frequency, and the maximum frequency. This function, readWAMIT is the function that actually writes the hydro data structure into that H5 file. So you just need to input your hydrostructure here in this function, and that's the only thing that you need to do, and it will write the .h5 file. This plot Vimeo is a post-processing function, and this function is just an example of the many ways that you can plot the output for Vimeo. So you can actually modify this function and to plot anything that you want from your VM, but the default version of this function plot the added mass, the radiation damping, the radiation IRF, the excitation force magnitude, the excitation force phase, and the excitation IRF for each body in heave, source, and pitch degrees of freedom. And this function is also useful to check your VM data before you run your WEC Sim simulation. We have some examples for Vimeo in the tutorial section and in the example sections of WEC Sim. So if you go to WEC Sim examples and Vimeo, you can see folders for the different VM solvers that we support with Vimeo. So, and you can find examples for each of the VM solvers. Also, we have a function called compare VM that you can use to compare different runs with different VM solvers. So remember also that the documentation for Vimeo is in the advanced features section of the WEC Sim documentation webpage. So as I just mentioned before, this compare Vimeo function can be used to compare different runs for the same body. So then if you have let's say VM results from WAMIT, Capitane, NEMOH, so you can use this function to compare the results between the different solvers to see how well they compare to each other. So now I'm going to give you some examples on how to use Vimeo. So if you want to follow along this tutorial, you can go to WEC Sim examples Vimeo WAMIT RM3, and that's where you can find this Vimeo script that we are going to discuss now. In this example, I want to talk a little bit more about the steady state representation of the IRF. It is desirable to represent the radiation convolution integral in state space form. This has been shown to dramatically increase computational speeds and allow utilization of conventional control methods that rely on linear state space models. So for the RM3 example, after you run Vimeo, this is what you get. So you get these plots with the normalized added mass and the normalized radiation damping, so for source, heave, and pitch. And you can see that you have results for the two bodies, for the float and the spar. So remember that the IRF function takes the radiation damping to calculate the radiation impulse response functions in this case. So here we can see results for the integral formulation and for the state space formulation of these functions. So if we take a closer look to these results, we can see that the match between these two functions, the integral formulation, and the state space formulation is not very good. So we can try to improve this a little bit. So for doing that, we can increase the R2 threshold to 0.99. Remember that the default value was 0.95, and when you increase the value to 0.99, you can see that the results for the integral formulation and for the state space formulation are more close now. So it improves the results substantially. So now if you're trying to increase that a little bit further, you can see that the improvement is not as different as the previous results with 0.99. So then you can find like a value that works for your simulation. If you want to use the state space formulation, you need to define that in your WEC Sim input file. You need to use the state space variable, and you need to activate it to use this formulation instead of the convolution integral formulation. So depending on your specific problem or the specific problem that you want to solve, you would like to use this formulation, so you need to specify that into your WEC Sim input file. Now, what happens if you need to change the upper wave frequency limit on the IRF? Maybe the VM hydrodynamic data is poor and needs to be cut off. So you can do that here in this parameter, this input parameter for the radiation IRF function. So depending on the VM solver, mesh quality, and size of your device, the hydrodynamic coefficients can be reported with noise and non-physical solutions. So you need to be careful, because if you use this kind of like poor VM results, this can lead to unstable WEC Sim simulations. So let's see what happens if you decide to cut off the frequency. when you when your cutoff frequency is sufficiently high, what you can see is that the normalized radiation impulse response function uh, tends towards zero, and that's a good result. But if your cutoff frequency is too low, what you can see is your normalized radiation IRF doesn't tends towards zero. So that's bad, and you will need to define a cutoff frequency that gives you this behavior here in the left. So you need also check the normalized excitation impulse response function. In this case, the function needs to tend towards zero when it is a good result. But here you can see that if the cutoff frequency is sufficiently high, you have that behavior, the excitation IRF tending towards zero. But if your cutoff frequency is too low, you have this other behavior where the excitation IRF is not tending towards zero. So you will need to correct this to have like better results for your WEC Sim simulation. That's all that I have for this presentation. For more information, please visit the WEC Sim website. And if you have questions on this presentation, please reach out to any of the WEC Sim developers on GitHub.